In this lesson 8.3, we're going to be graphing what we call reciprocal functions. We've been working on rational stuff, rational expressions, things like that. In the next section, we're going to be graphing any old rational function, but we're kind of starting you off with like step one, which is the easiest type of a rational function, so we can get used to it. So we're going to start talking about vertical and horizontal asymptotes. We've talked a little bit about asymptotes before. Those are the lines that you can get really, really close to, but your graph won't actually touch that line or cross over that line. So we're going to introduce first the idea of what exactly a reciprocal function is, and it is this. It's an equation of the form f of x, remember that's our function notation, equals c over a of x. All right, and I'm going to explain exactly what those pieces are, where c is a constant, so just some number, maybe a 2 or a -4 or something like that, and a of x is a linear function. Okay, so it's a linear function that's not equal to 0, because we know our denominator can't be 0, otherwise it's undefined. All right, so a linear function has just an x, no x squared, anything like that. So like x plus 3, or like 2x minus 5, or something like that. The biggest power is 1. That's what makes it linear. So that's our definition. We're going to take a look, just like in every graphing section, at what the parent function looks like, kind of the original before we make any transformations. And so here's what I can give you about the original. The parent function that we are talking about, the simplest one of them all, is just 1 over x. Okay, so the easiest constant we can put up there is 1, and the easiest linear function is just an x. The type of graph it is, this is a new word for us, it's something called a hyperbola. And when you see the graph in front of you, it will hopefully kind of explain what shape a hyperbola is. I couldn't explain like a parabola in words, it's best to just see it, so same thing with the hyperbola, so we'll get there in just a second. Domain and range, for this one specifically, both of them, both the domain and range, are all non-zero reals. So what that means is that x can be anything but 0, y can be anything but 0. Okay, and that's because we have asymptotes at x equals 0 and y equals 0. Okay, sorry, these two lines are getting kind of smudged together. An asymptote means that's a line you'll get very, very close to, but you'll never touch. And so since you'll never touch this line, we restrict it from our domain. And since you never touch this line, we restrict it from our range. Okay? Intercepts, there are none. Since we never touch this line, we never touch this line. Remember, this is our y-axis, this is our x-axis. If we never touch those lines, we're not going to have any intercepts. And it's not defined here, this one specifically is not defined when x equals 0, but really it's whenever the denominator is equal to 0. So whenever the denominator is equal to 0, our reciprocal function is going to be undefined. So that's a big important idea that we'll talk about specifically in example 1. So here's what our graph looks like. This is what a hyperbola is. There are two different, I call them boomerangs. The shapes, and you'll see the shapes look just like boomerangs. So it kind of curves along this line and then just scoops out over this way. So there's one of the pieces. So see how it drags along this line and drags along this line. That's why we call it an asymptote. And then the exact same thing is going to happen in the lower left. Okay, so we've got these two asymptotes, x equals 0, which is this line. See how down here and up here my graph is getting closer and closer to that line without actually crossing it. And so there's no y-intercepts. And then this line right here, this is my x-axis, which is the line y equals 0. My graph is getting closer and closer to that line without actually crossing it. And so that's why I don't have any y-intercepts. So that is the original. This is my parent function, 1 over x. And we'll talk later about how the transformations will change the graph. Move up, down, left, right, scale, flip, all of the fancy things that transformations can do. Okay, so This I wrote down just right here. The domain is limited to values for which the function is defined, and the function is not defined whenever the denominator is equal to 0. So we're going to practice that with example number 1. So what we want to do is we see this denominator, here it is, x minus 1, and we know the denominator cannot equal 0. Okay, so we treat this the same way as we would treat an equal sign. We do all the algebra the same way. So we would just add 1 to both sides. And so this tells us that x cannot equal 1. If x were equal to 1, then this thing would be undefined, and so this is called a domain restriction. It means that my domain can be any value of x that I want, except for 1. Okay? This one, I can do the same thing. I take my 3x plus 2, that's my denominator, and I know it can be anything but 0. So I do whatever algebra I need to do to get the x by itself. So 2 steps this time. Subtract 2. So now we know that 3x can't equal negative 2, and then divide both sides by 3. Okay, so here, x can be anything we want except for a negative 2/3. That's the one place where my function is undefined, and again, we call that a domain restriction. So these two things right here, we call those domain restrictions. Okay, so that's my first idea. First idea is these domain restrictions, and when we're looking at the equation itself, like I said, all you have to do is set the denominator equal to 0 and you can figure out where it's not defined for x. You're also going to have horizontal asymptotes. So we've got these graphs in front of us for example number 2, and we're going to use just the graphs to identify the asymptotes, the domain, and then the range of each function. Okay, so the asymptote, like I said, is a line that your graph is going to get really, really, really close to, but it's not actually going to touch. And so you can see somewhere like right around here, that's a vertical line that your graph is getting really, really, really close to, but it's not actually going to touch. And then right about here, there's a horizontal line that your graph is going to get really, really close to, but not actually touch. Okay, so horizontal asymptote, vertical asymptote. So this line right here that I sketched in is the line y equals negative 2. All right, so y equals negative 2. You can see because it's scaled, so it's scaled by, that's negative 2, and the next one is negative 4. So this line right here is what my graph is going to get really, really close to, but not actually touch. That's my horizontal asymptote. Remember, y equals lines are horizontal lines. And then this line right here, if this is 2 and this is 4, we're going to say that's 3. So x equals 3, that is my vertical asymptote. So I'm going to write those things actually, just so we know those vocab words. Okay, a horizontal asymptote and a vertical asymptote are my lines, and I kind of sketch those in there. Now, it's not like those just mysteriously appear by looking at the graph. There's actually a way to figure it out from looking at the function too. So my horizontal asymptote of negative 2, see that minus 2 right there? It's not a coincidence. The number hanging on the end is your horizontal asymptote. If there is no number hanging on the end, it's 0. Then if you look at the denominator, remember doing the domain restriction? If we set x minus 3 equal to 0, we would get 3. And so that's my vertical asymptote. All right, we'll talk more about that on the next page. We also want the domain and the range, and so the domain and range is everything but the asymptotes. So the domain is any x value except for 3, and then the range is any y value except for negative 2. Okay, so once you figure out the horizontal asymptotes and the vertical asymptotes, you know exactly what the domain is. Or vice versa, if you figure out what the domain and range are, then you can work backwards and say, oh, if x can't equal 3, then x equals 3 must be the asymptote. So you kind of get the idea, whichever one you find first. And like I said, it's not just from the graph, you can see it in the equation. So remember x lies, so since that's a minus 3, the domain is, x can't equal positive 3, and then the minus 2, y doesn't lie. So let's look at the next one. So we can see it from the graph, but like we said, we can now also see it from the equation. So for the horizontal asymptote,
good morning.
We can go off the same idea that we had over here is, first of all, I mean, we noticed it on the graph, but I also told you it's exactly what number is hanging out by itself at the end. So since there is a 5 hanging out by itself at the end, that means that our horizontal asymptote is 5, which you can also confirm by looking at the graph. So we go up here to a height of 5, and you can kind of sketch in. You see that is, in fact, your horizontal asymptote, that these are kind of dragging along to the left, dragging along to the right. Your vertical asymptote, and I'm abbreviating, sorry, those are both very long words. We've got x equals, and then remember x lies. So here there's an x plus 1. So that means that your horizontal asymptote would be x equals -1, because you're always doing the opposite. And like I said, you've got the graph in front of you, you can kind of confirm that. If we find our -1, you can dot that line in, and you can just kind of confirm, make yourself feel better inside that you did a good job of finding the vertical asymptote, because you can see it on the graph in front of you. Okay, then like I said, once you have the vertical asymptote and horizontal asymptote, very, very easy to identify domain and range. Since the vertical asymptote is x equals -1, that means the domain will cover anything but -1. And since our horizontal asymptote is y equals 5, that means our range will cover anything but 5. All right, so we're kind of tiptoeing our way towards making our own graphs here. We figured out how to find the domain restrictions, how to find the range restrictions, horizontal and vertical asymptotes. So let's take a look at the transformations that we can talk about, and then we're going to graph a couple of these. So transformations. We can see, you know, this k on the outside, we know what that affects. We know that does a horizontal asymptote. And then this h down here, we know that's going to do a vertical asymptote. So a horizontal translation, remember horizontal is going to move you either left or right, and that's the effect of the vertical asymptote. So we've got h units either left or right. Remember, x lies, so it's the opposite of what it looks like. So if it's if it's x minus something, you're actually going to the right, and if it's x plus something, you're actually going to the left. All right, so just a little reminder here that x lies. So it's the opposite, which I meant to make that an asterisk, and then it kind of looked like an x. We're just going to go with it. All right, x lies. And one thing to keep in mind is that your vertical asymptote is now going to be x equals h. So notice here this formula is an x minus h, so it's already kind of accounting for the fact that x lies. All right, so x equals h. So if it's an x minus 2, the horizontal asymptote is 2. If it's an x plus 2, the horizontal asymptote is -2. Because like I said, this negative accounts for the sign change there. Vertical translation is either up or down. It's just this value on the outside here, the k. So you either go k units up or down. But don't worry about y lying. Y does not lie. Y tells the truth. And so if this is positive, you're going up. If this is negative, you're going down. And then the horizontal asymptote ends up being that exact value, y equals k. Okay, then the last thing is the orientation and shape. One thing that we really haven't talked about yet, that's this value right here. It has to do with a. If there's not just a 1 up there, then it's going to change the shape of your graph a little bit. Like always, it's got either a stretch or a compression, or it could be flipped. So if a is less than 0, that means your graph gets flipped upside down. And we've seen these exact same transformations over and over and over again. You just get to see how they affect different shapes. And then, of course, if a is bigger than 1, then that is a vertical stretch, just like always. And then if a is somewhere between 0 and 1, like a fraction, remember it's a vertical compression. And I'll show you exactly what the stretch and compression look like when we look at these next two examples. Okay? So this one, we're going to graph each function, state the domain and range. So let's actually start with the domain and range because I think that'll help us graph. So for my domain, remember x can equal anything but the horizontal asymptote. And since x lies, the horizontal asymptote is the opposite of what you see here, which would be a -4. In the range, the y value can be anything but the horizontal asymptote. All right, so the horizontal asymptote is a 1, so y can be anything but 1. And then let's take a look at this -2 and what that tells us. So the -2 means that we are going to be flipped upside down and then stretched by a factor of 2. Okay, so that is what all of my pieces tell me there. So let's set these up. Okay, and I'm going to show you, very importantly as well, how you show your asymptotes on the graph, because that's very, very important. Okay, so x can't equal -4, so we're going to go 1, 2, 3, 4 units, and what I want to see every single time is a dotted line, kind of marking the boundary of where your graph can't go. Okay, so you're telling your graph that it is not allowed to cross that line. And then y can't equal 1, so we go up to 1 right there, and we're going to do the exact same thing. We're going to sketch in a horizontal line showing your graph where it is not allowed to go. Okay? So let's actually, I'm going to extend everything a little bit farther that way just so we can see more of the picture. Okay, so upside down. I want to show you something based on the original graph. I'm going to flip back to our initial. So see how here, when this is positive, we're in the upper right and the lower left. If we flip our graph upside down, we're going to be in the lower right and the upper left. So that's what's happening here. And then we're also stretching it by 2. And what ends up happening when you stretch it by 2 is that everything gets a little bit farther away. So see here, I came like pretty close to the origin right here, but the bigger your number, the farther away you're going to be, okay? So let me sketch in our graph. So since it's upside down, we're going to be down here. So we're going to sketch along here, and then we'll curve and then go along here. And since this is a 2, I'm about twice as far away from this center as I was in my original graph. And then I do the same thing over here. I'm going to glide along this line and then glide along this line. And this, the whole stretching it by 2, that's just kind of eyeballing it. So you want to be about as far away right here as you are right here. Doesn't have to be flawless. The upside down part is very important. The asymptote part is very important. All right? Let's look at the next one. This one, my domain, remember x lies, so x can be anything other than the opposite of this number, which is a positive 1. And then for my range, y can be anything but this number on the outside here, so that's a -2 because y tells the truth. This is positive, the 1 is positive, then we're going to talk about that 3. So it is not upside down, it is right side up, so I'm not even going to write that down because we would assume that it was going to be right side up. And then this is really like having a 1/3, and since a 1/3 is a fraction, it's going to be a compression. Okay, so what the compression means is with 2, I'm kind of far away from this center right here. With a 1/3, I'm going to get closer to it. All right, that's really the only difference that you'll see with a stretch or a compression. So start with my axes. So x equals 1 is right here, y equals -2 is right here. I'm going to sketch in my vertical asymptotes. So my graph cannot cross this vertical line of x equals 1, and my graph cannot cross this horizontal line of y equals -2. Okay, it's right side up, so I'm going to be in the upper right and the lower left, and we use these pink lines, not the black lines, not the axes. And then since it's a 1/3, I'm going to get pretty close to where the pink lines meet. Okay, compared to the 2. The 2 takes me a little farther away, the 1/3 takes me closer. All right, so sketch in here, get pretty close, and then turn down. All right, so those are a couple of examples of your graph there, and I think that that is where we stop. Yes, it is.